I'll tell you something about the organization, and then I start with the first topic. Okay, foundations of cryptography. What are we talking about? Cryptography is the study of techniques for securing digital information transactions and distributed computations. It's something that some of you, I'm sure, currently use it or have used it already this morning, and hopefully you didn't notice it. Because that's the goal of cryptography, provide security without you actually noticing it, mostly. As usual, if things fail, then you notice it. Sometimes it gets a little bit more complicated. But basically, cryptography is one of the fundamental techniques, fundamental areas that underlies the IT security of today's infrastructure, IT infrastructure. There are other techniques involved, but many at some point also use cryptography. So in this course, I will focus on the cryptographic techniques. Every once in a while, I'll explain how they fit into larger applications, but our focus is clearly on the cryptographic techniques. Okay? And so what are the main goals of cryptography that we want to achieve? There are usually three things that are mentioned, although today we have many more goals, but we'll focus on these three goals. The first one is called confidentiality, which means that the avoidance of unauthorized disclosure of data. You want to keep data private, confidential, only you should be able to understand the data. What we will not try to achieve is, for example, you have a conversation with somebody. We are not going to try to hide that you have a conversation. We are trying to hide what you are talking about. Okay? But that applies to conversations that you have by email, say, in social media, whatever. But it also applies to if you store data somewhere. If you outsource data on an untrusted server, you don't want the server provider to be able to understand your data. He knows that you stored the data there. You probably paid for it, right? So he knows that you store data there, but you should not be able to understand the data, be able to read the data in plain. So that's the first main goal that we have. That's called confidentiality. The next one is called authenticity, which is the ability to determine that statements, policies, and permissions issued by persons or systems are genuine. They come from the person, from the system you think they should come from. Right? If you talk to somebody, you want to be able to verify that you talk to the right person. If you talk to your bank, you want to be able to verify that you are really talking to your bank and not some fraudster that tries to impersonate your bank to get hold of your money. Okay? If you set up a meeting, you want to be able to determine that you are really talking to the right person and not somebody else. Authenticity and confidentiality are different goals. They require different techniques to achieve. I will explain this in more detail once we go from confidentiality to authenticity. Many people, also people who work in industry, think that if they achieve confidentiality, they also achieve authenticity. That's not true, not necessarily true. The techniques that we develop for confidentiality are not meant to achieve authenticity. In practice, they often do because they combine different techniques. Okay, but this is not necessarily true, and it is very important if you apply cryptography to know the goals that you want to achieve so that you can choose the right technique for that goal. The last thing that we will be talking about is non-repudiation, the assurance that someone cannot deny the validity of something. If you sign a contract with somebody, right? And you do that electronically. You do a digital signature. You want to make sure that the other person cannot eventually deny having signed your contract. Right? You sign a contract for purchasing a bicycle, say, and then you already send the money, but then the other person said, well, no, there is no contract. I keep the money, I never received it, and there was no contract. Right? So, and that is meant by non-repudiation. As I said, these are the three things, the three goals that we focus on. There are many other goals that we try to achieve with cryptography today, many also dealing with issues of privacy, that you keep your data. Well, confidentiality obviously has something to do with privacy, but there are many other things that we want to achieve with regards to privacy. Okay. So as I already said, cryptography is an indispensable tool to protect data achieving confidentiality, authenticity, non-repudiation. It's used by most people every day. Whenever you use your wireless LAN, you probably use cryptography. Right? If you look at your router, there's something, AES, something on the back of it. Well, that's cryptography. Right? If you use e-banking, e-commerce, whatever, there's cryptography involved. If you use the wireless LAN here, eduroam, there's cryptography involved. You have a certificate. Without that certificate, you cannot access the wireless LAN, so you always use it. For example, it's an integral part of important standards, for example, TLS, that you always use, often use when you browse. Whenever you see that you switch from HTTPS from HTTP to HTTPS, that usually means there's cryptography involved now. Right? You switch to certain standards that are embedded in these protocols. Okay? So it's really one of the major tools that we use today to achieve security. At the same time, it's important, but it's also very brittle. It's easily rendered completely insecure by misuse. You use the wrong tool for the goals that you have. You want to achieve authenticity. You use tools to achieve confidentiality. That's not what you get. But it's also insecure by, well, that is also covered by specification. What do you want? You specify your goals. But it's also rendered completely insecure by programming errors or protocol oversights. Many things, whenever you see that there was some security incident, there usually was some programming protocol error. Buffers were too small, or buffer overflow wasn't handled correctly, things like that. So it's very brittle, so you really have to be very careful in applying cryptography. We are not talking about in this course how to apply cryptography, but what we want to make sure is that the things that we provide for the application is as good as possible, right? And also as stable as possible. Okay? So we'll start out with things that are very, very good, right? And the hope that since they are very good, they're harder to destroy or harder to misuse. This is not always the case. In fact, because they are so sometimes so involved, it's hard to actually apply them as an engineer that embeds them into more complex protocols, say. But so what we want to have something that we can, before we actually apply it, no, this is really good. So how do we do that? The one thing that we need to recognize immediately is testing cannot show the security of a crypto system. You cannot simply run tests. The reason for this is very simple. If you run tests, you have to realize, okay, what is the adversary going to do? What is he trying to do to break my system, to circumvent the the barriers that I build around my data. And then you rely on you being, or me being, as clever as the adversary. And you should never do that. You should always look. One principle of cryptography is the other people are smarter than you are. Okay? The adversaries are more powerful and they are more smarter than you are. So you are dealing with people who really know what they are doing, and because you lack the imagination for certain attacks doesn't mean that other people also lack that imagination. Right? And in testing, you can only test certain things. And you have to, look, I imagine that they tried to do this. That's not good enough, because they may come up with some really weird, really strange ideas that work. Okay? So testing is not good enough. So what we'll do and must do is we must use mathematical modeling and proofs to argue that a crypto system satisfies the desired security properties. A mathematical proof that says this is secure, usually under certain assumptions. I'll come to that point later. Okay? Which means that it's not a lack of imagination that leads us to thinking that the systems are secure, but we have a hard mathematical proof for it. Okay, so, and that also means that often we'll see that if we want to achieve sort of security that is where we can say it's secure, period. This is very hard to achieve, and it's very expensive and inefficient, and usually also not necessary. Okay? To make things easier, to make them more efficient, and sometimes also to just achieve these kind of things, we must make certain assumptions. But if you do so, we must make these assumptions precise. And we must make at least plausible why we think they are correct, or why we think we can make those assumptions. These assumptions usually are of the type, certain problems are hard to solve on a computer. And not just by you and me, but everybody. So there are no algorithms at all, efficient algorithms that solve these problems. This is our assumption, and then obviously we should have good reasons why we think that these problems are hard to solve. Good reasons being, for hundreds of years people have tried to solve it, they failed. Okay? Or we embed it in things like complexity theory. Right, the study of hardness of problems from a theoretical point of view. So we use mathematical proofs, we use precise and plausible assumptions. Starting out from these assumptions that we state, we have precise goals that we want to achieve, and then we show that we design a system, and then we show that given those assumptions, we really achieve those goals. Okay? And prove that. We'll go into how we do that. This is one of the major things that I'm going to talk about in a couple of weeks. That's a nice thing about this course. We basically use the same technique over and over again. Right? We do proofs, but the proofs always look, on a high level, they always look the same. Right? I will always start my proof, well, sometimes I forget to do that, but I will always start my proof, let A be an arbitrary but fixed efficient adversary against something. Now I do da 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 da. So it's always going to be the same. Okay, good. There are certain basic principles that make the things that I just mentioned a little bit more precise. Those are the principles that we really rely on in cryptography and to some extent in security as well. The first principle goes back to a Belgian named Kerkhoff, who formulated this principle already in the 1890s, so well before modern computers. But he knew about the basic techniques or the basic construction to use to achieve confidentiality, and hence he formulated the principle in that context. And it says that an encryption scheme must not be required to be secret and must be able to fall into the hands of the adversary without inconvenience. And you can replace encryption scheme by any other cryptographic technique. We never ever keep the techniques that we use private. We make them public. We are using this. And there are two reasons for that. The first is these things are standardized. Everybody should be able to use it. You cannot standardize something that's private, that's hidden. Okay? The other thing is, although we have mathematical proofs for the security of our crypto systems, we still rely on these assumptions. And sometimes we may fail. We may just make little errors in our proofs. Mathematical proofs can be wrong. Okay? By making all these constructions public, we say, look, guys, here's my proof, here's my construction, try to break it. Right? And if then people after 12, 15, 20 years have still not been able to break it, but everybody knew what to break, then you can be quite confidential that this is a good one. Right? If you ever use a system where people tell you, look, this is very good. It's so good that I'm not going to tell you what it is. Don't use it. Big companies have done that in the past. All these systems disappeared eventually because they were wrong, weak, and to some extent stupid. When we now, like there is in the United States, there is the so-called National Institutes for Standards and Technologies that standardize many of these things. They do very elaborate selection processes to come up with the schemes that they recommend, where people can really look at them in detail, try to break them, and after years of such a selection process, they eventually say, look, this is the winner. And that's a good practice. Okay? So that goes back to Kerckhoff. The first principle then, which I already mentioned, is we must formulate a rigorous and precise definition of security for a given cryptographic primitive. When I say confidentiality, well, what does confidentiality mean? Well, we have a rough idea what we mean. Well, only I should be able to understand my data, but we need to give a precise definition that also takes into account what kind of information may be available to adversaries. But we should be very generous in telling or stating what adversaries can do and what they may know. Simply, the next principle said if the security of a cryptographic construction lies on unproven assumptions, this must be stated precisely. Right? If you say, look, this is only secure or can only prove it given this assumption, you must state that assumption precisely, what you really mean by that. And then cryptographic constructions, as I said, require rigorous proofs of security with respect to the security definition, first principle, and the second principle, namely the underlying assumptions. And since you want mathematical proofs, you cannot achieve a mathematical proof without precision. Okay, so let me talk about the assumptions. What kind of assumptions do we make in cryptography? And these assumptions basically fall into two categories. The first category are concrete assumptions. They state the following precisely stated mathematical problem is hard to solve. I will explain what hard to solve means because we also have to define that. What does it mean, hard to solve? And an example for such a problem is factoring integers. If I give you a large number that is a product of two prime numbers, my assumption then would be it's hard to find, given that number, to find the prime factors. And then I have to tell you what hard to solve means. how the numbers are generated, blah, blah, blah. There's lots to cover there, okay? The other one is, say, computing discrete logarithms, which I may explain at some point during the course what that is. So these are precise problems, concrete problems that we think are hard to solve. Factoring, the first people who looked at factoring, well, in earnest probably was Gauss. And he wasn't able to solve it. And since then, which is more like roughly 200 years ago, people have made some progress, but not to the extent that we think that at this point that factoring is easy to solve. Well, some people think it may eventually turn out to be easy to solve. Assumption is always about our current knowledge or lack of knowledge. Okay? Currently, we don't have any good algorithms to factor. That may turn out to be wrong while I speak. Right? There may be somebody somewhere who comes up with a brilliant idea that has evaded mathematicians for the last and computer scientists for the last 200 years. But it may be out there. Yeah? As a side remark, hard to solve is always about certain types of computers. And this is important. I will not go into details, but factoring integers, many people think it's hard to solve on classical computers. We know it's not hard to solve on quantum computers. But as of today, we are not able to build quantum computers of the relevant size to actually implement those algorithms on a quantum computer. If you're interested in these topics, there may be courses in the next semesters where I really go into this type of thing. Okay, so this is concrete problems, okay? And as you already may have noticed, I said, well, some people may think that factoring is easy, so they already have doubts that factoring is a good assumption to make. Other people think, well, no, factoring is really a hard problem, but it's like a matter of taste. But I would say that our confidence in general that certain precise, concrete problems are hard to solve is limited, okay? But there are other assumptions that we can make which are more plausible, namely the assumption that some hard problems really exist. We don't know what they are maybe, but we believe that some hard problems do exist. And this relates to one of the, probably the most famous unsolved problem in theoretical computer science, is P equal to NP? Are there problems that lie in this class non-deterministic polynomial time that cannot be solved on a deterministic Turing machine? Our confidence that this statement is true, P is not equal to NP, is much better than our confidence that factoring is hard. Okay? So we may try to base cryptography on these types of assumptions, very general ones, okay? And build from these assumptions our crypto systems. And then you say, well, okay, now when you actually instantiate the constructions, you will use a concrete problem, right? So, okay, now I think that the following problem falls into this category, and now I may base my system on this problem. Okay? Then somebody comes up with a brilliant idea. The problem turns out not to be of that type. That's bad enough. If you build a huge system based on this, you have to redesign everything. But there are alternatives, because you can use some other problem that falls into that category that is not affected by this new research findings. Okay? You can, well, this problem turned out not to fall into that category. We have tons of other problems. So we use one of them. and redesign our system. Right? So having these general assumptions leads to much more flexibility. Right? We can use this, we can use that. Well, if one of them goes out, is thrown out the window, okay, it's inconvenient, it's a pain, but it's not that everything breaks down. We can move to something else. In this course, I will focus on this here, on the general assumptions. That's why the course is called Foundations of Cryptography. So foundations, well, it's really about the basic constructions. In that sense, it's foundations. But also it's foundation because we look at really the foundational questions. What type of assumptions do we need to make so that cryptography exists, that we can build it? Okay? And not using a specific one, but these things. As a side remark, it will turn out that the P is not equal to NP is not sufficient to get cryptography. We need something more complex. What I will talk about for almost half of the course is the assumption that so-called one-way functions exist. And it turns out that once and then there are many candidates for one-way functions, right? Concrete candidates. Turns out that one-way functions, if they exist, we can build almost anything that we need in the area of so-called private key or symmetric key cryptography. But there is another area which is called AES is an example of these things. If you heard about SHA, SHA-2, SHA-1, SHA-3, Ketchak, they are all symmetric cryptography. They are things like that. This is called private key encryption schemes, message authentication codes. They all exist once we have one-way functions. But there's another area of cryptography which is called public key cryptography, RSA, Al-Jamal, DSA. Those typically cannot be constructed using just one-way functions. We need even more complex assumptions, namely that so-called trapdoor functions, trapdoor permutations exist. But be careful again, getting ahead of myself. For digital signatures, the existence of one-way functions is enough. Okay, so when we'll see that how we can actually build these things. The constructions that I will tell you, I start out with a one-way function, and then from that, through several steps, for example, I will build secure private key encryption schemes. The constructions, as I explain them, you will not find as such in practice. Because then you have, in practice, you will instantiate your one-way function by something specific. And then what you'd often do is you take the basic ideas that I present in this course, and then you optimize them with respect to the concrete problem, the concrete one-way function that you start out with. And say, okay, then I can make this more efficient, I can make this more efficient. For this, I have a much better algorithm, so I can here a shortcut, but always prove that the shortcut doesn't destroy security. So the basic ideas are usually better and best understood if you start out from the general assumptions, and then if you then want to instantiate it, you start from that and make things more efficient using the concrete stuff that you have. Okay? So don't expect anything that you can immediately apply. That's not true. But the techniques are things that in almost any construction that you will see is relevant. Okay, so as I said, we mostly follow two. Sometimes I switch to one just to give you examples or make things more concrete. Okay, and let's talk a little bit about the topics. As I said, we'll talk about confidentiality, authentication, and non-repudiation. So what we'll do, we will see that from one-way functions or one-way permutations, we can construct private key encryption schemes that are secure. As I said, from trapdoor permutations, we'll construct public key encryption schemes. This refers to confidentiality. We'll design so-called message authentication codes from one-way functions, one-way permutations. This refers to authentication. And we'll design digital signature schemes from one-way functions. Digital signatures provide authenticity and non-repudiation. Message authentication codes only apply authentication. Although, if I want to have really good private encryption schemes that are really strongly secure, security is not a 0-1 thing. You can have different levels of security. If you want to achieve the sort of what we consider today the strongest level of security for private key encryption schemes, which is called int CCA2 security, then you actually combine things from confidentiality and authenticity. But we'll see how authenticity must play an important role if we talk about this really strong security requirement, because that really talks about, to some extent, also about authentication and authenticity. Okay. Let me tell you a little bit about the prerequisites for this course. Cryptography, to some extent, is applied basic probability theory. We always talk about probabilities here. The reason for that is simple and obvious. What does it mean for, or what would you consider to be a serious break of security for a system? That an attacker is able to break something always? That doesn't make sense. If he's able to break something in 0.0001% of the cases, and you talk about, say, credit card transactions, 0.0001% of all credit card transactions per day worldwide is still a large number, right? So you want to be sure that the probability that an adversary is able to break this thing is really, really, really tiny. Right? Because otherwise you could be one of the unlucky ones, falling into the category of 0.00001. Huh? Bad. So when we say that an attacker is not able to break a system, we necessarily have to talk about his probability of achieving what he wants is really tiny. Right? Probability. Okay? And we don't do tests. We don't do like empirical studies, right? That he wasn't able to do that more often. That's not going to do it, right? Probably you don't want to participate in such an empirical study with your money, right? I wouldn't do that, okay? Maybe Bill Gates does it for like 1% of his money, but I wouldn't do it. So probability theory is something that we need, and actually it turns out that the things that we want to achieve, we need to formulate it using probability theory, and we also need to have algorithms that can use random coins. They use random bits. They are probabilistic algorithms. Okay? And also, we talk about, today already, we talk about keys and secret keys. If you talk about something that's secret, you talk about probability, actually. You talk about, more precisely, you would talk about information theory, things like entropy, how much uncertainty is in something. If you want to keep something secret, right, that means there's a lot of uncertainty for the other person what you actually use, okay? If you use something secret and there's not a lot of uncertainty in it, and I know you'd use one of two things, forget it, If you use a personal identification number, a PIN, well, it's 4 digits, right? If you use just 1 digit, the uncertainty is like 10, right? Or basically, we would actually formulate it in number of bits that you need to know. Well, that would be slightly above 3, right? So there would be 3 bits of uncertainty. 3 bits of uncertainty that you can even do by hand, basically. And if you have a computer that does it for you, 3 bits of uncertainty, it's nothing, right? So if you talk about secret things, there needs to be lots of uncertainty. And there needs to be lots of possibilities and from which you pick something according to a probability distribution. Probability theory. Okay, we also need, of course, algorithm design. Although we are not using anything fancy. At some point I may say, well, this we can use by using standard data structures, but mostly I'm not focusing on very precise algorithmic statements. Basic complexity theory, all I use, I define precisely, but it's very helpful for you if you have a basic understanding of things in complexity theory. In particular, my proofs, security proofs, will always be proofs by reduction. And if you remember complexity theory, undecidability, or NP completeness, NP hardness, you use reductions. At some point, you first, well, actually, even in the beginning, you use it, at least for NP completeness, you use a reduction also. We use more refined reductions. So from the structure, it's kind of the same. Reduction simply means, give me a solution to this problem that I can use as sort of a black box. I can call that as a module. Then I can construct also a solution for the other problem. Right? And I don't want to know what this other thing in detail does. I just need sort of the input-output behavior of it. And I can call it with a certain input. It gives you the output. And I can use that and build another program around it to solve my other problem. That's a reduction. We kind of have to refine it because we use probabilities sort of so that we are not usually saying, if you give me something that always solves this problem, then I can build something that always solves this other problem. Instead, what I will doing is, if you give me something that solves this problem with a certain probability, I can build something else that solves this problem with a related probability. Okay, and they have to also relate those probabilities. So that makes life a little bit more difficult. In detail, it forces you to look at things more closely, usually. Okay? We'll come to that when we see the first proof of this type. Very basic number theory. Sometimes I go just as an example, what kind of thing could be a one-way function, what kind of thing could be a trapdoor permutation. I will go to number theory. Number theory is basically our source of mathematically hard problems for cryptography. Need not be number theory, could also be coding theory, but most of the stuff that we use today is based on number theoretic problems, like factoring, discrete logarithms, elliptic curves, geometry of numbers, algebraic geometry as a whole, these types of things, but it's very basic. The most important things I really is you must have understanding of complexity theory that helps, and you must be able to understand basic probability theory. And if I say basic probability theory, I really mean basic. I'm not talking about continuous distributions. I'm talking about discrete distributions. I need things like independence, stochastic independence. I need conditional probabilities. I need a Bayes theorem quite a bit. These things like union bound, total probability, stuff like that. So very, very basic things that if I had to teach it to you, I would probably need 90 minutes and we are done. Okay? But I assume that you know these things. If not, there are good books for it. Okay? If you need pointers to good books, let us know. We'll put a few on the web page. Okay. Good. Any questions about this? If not, then I'll move on to the formalities, and then we take a short break, and then we'll start. Okay. So everything again is different this semester. Everything will be in person again, hopefully, and hopefully we can keep it up. So lectures, tutorials are all in person. As they used to be. And everything related to this course can be found in Panda. So go to Panda, there you find the lecture material, you find the exercises, you will find a discussion forum, and you will find videos. We'll actually record all courses. And actually, if Techniques allows us to do that, we'll actually stream the courses as well. But afterwards will be made available. So you can also look at it in later on. But in a video, you cannot ask questions, right? Keep that in mind, right? So I still think that it's useful to have these videos, to go back and see how I explain things maybe, and maybe slow down a little bit or run it faster. I've heard about that in the past, that people do that. So obviously I don't talk fast enough. So you can watch the videos and see what I talked about. We also have this forum where you can ask questions, and we'll try to answer them. But again, the forum it complements asking questions in the tutorials and in the lecture notes. It's really complementing them. It cannot really replace them, I think. The tutors will answer the questions and join the discussions. And if you have any trouble, let us know. And in the forum, you can also post anonymously. So we preserve your privacy. So if you think that, if you want to say that something was really explained really, really bad, poorly, say so, okay? I'm actually happy to get that kind of feedback. Also, I should say there is a complete set of lecture notes for the course that will be made available online. These are about 200 pages long with complete proofs, detailed proofs. Again, this cannot replace the course. In the course, when I explain a proof, you really see how I develop a proof. And I may give you intuitions that are not necessarily in the lecture notes. Then the lecture notes would probably be 400 pages long, and 200 is already good enough, I think. But it covers the technical stuff. And sometimes it covers basic intuitions. But here I can give you much more intuition, and you see how a proof develops. Okay? So that should also help you. So you get lots of material, use that material wisely. And that implies use it weekly. And to do that, we also have these exercises. We have two types of exercises, type 1, type 2. They are independent, formally independent of each other. The type 1 exercises, they deal with the most recent lectures, and it's designed to help you to comprehend, to understand what I said. They usually you should be able to solve them relatively quickly. Not if you didn't come to the course, not if you didn't look at the lecture notes and also didn't look at the videos, then you will not be able to solve them, probably. But if you did that, then they should be quite easy to solve, usually. Don't think that solving something is easy to solve means that you always do it quickly. I have thought about things for a week before I realized this was real easy. Okay? So sometimes you just get stuck. Okay? You learn a lot by getting stuck. Right? You try to find other ways. You think about things more globally, and you find out many things. Eventually, you find out that all this was unnecessary for this particular question or exercise or problem, but it may help you later on for other things. So that's a good thing. Sometimes it's a good thing to do. It's annoying anyway, but never mind. Okay, these type 1s are released every Thursday and are due on the Thursday next week. They are mandatory, which means that you need to achieve points in order to take the exam. So they are Studienleistung, right? Whatever that means in English. They must be solved individually, not in groups. And the first type exercise is available sometime today or is already available on Panda. There you see, as I said, you see also the other material. The type 2 exercises is designed to deepen, broaden your understanding by asking more involved questions. Potentially also spanning several weeks. This is good, right? You want to connect things that you learn over the several courses or several lectures. They are more time expensive and may require you to come up with the right idea. Sometimes you don't. Well, this happens to us all the time. Right? Such is life. They are released not on a regular basis, and you will have more than just 1 week to solve them. You have more, like 2 to 3 weeks. That gives you time to think about it, digest the question, think about it, try alternatives, and see whether you can come up with a good solution. They are not mandatory, but solving them grants you a bonus for your final grade. So, but they will not be able to get you from failed to pass. You need to pass the exam, and then we'll look, well, you get a bonus because you solved some of these type 2 exercises. And they can be solved in groups of 2 to 3 persons. Okay? Everything will be graded, obviously. So type 2 exercises can be painful fun. Okay. Okay, what are the concrete requirements? The course achievement based on the type 1 exercises. At least 70% of the weekly type 1 exercises has to be passed. I really want you to pass more than just 50% or so. You have to follow the course until the very end to pass it. Because you have to follow the course until the very end to pass the exam. If I do an exam and after like half of the course, or contents of half of the course, you say, well, no, I don't know anything anymore. That's not good enough. Right? And hence, you also need 70% here. It's probably going to be 9 out of 12 exercises. And a weekly exercise is passed if you reach at least 50% of the points. Okay? So overall, you need something like 1/3 of the exercises over the course, roughly. So it's not asking for too much. And as I said, Studienleistung is necessary for the participation in the exam. We need to check a box afterwards if you passed it. If you don't check the box, you will be deregistered from the exam automatically. The bonus system is as follows. This only, as I said, refers to the type 2 exams. If you have 50% of the points in type 2 overall, you improve your grade by 1 grade step if you pass the exam. And if you have 70%, then you improve by 2 steps. Good. Actually, if you do that and you really solve them, usually I have to tell you after the exam that you cannot use your 2 bonus steps because your exam was very good anyway. And you cannot get a better grade than 1.0. Right? So these things really prepare you for the exam very, very well. Also the type 1, but if you want to get into the range of 1.0, 1.3, 1.7, then this year really helps you. Not just because of the bonus, but because you really understood the material and should be able to pass the exam easily. Okay, the exams will be oral exams. There will be 2 blocks where you can take the oral exam, one at the start and one at the end of the semester break. So one probably end of July, the other end of September, early October. The exams are similar. Each exam is kind of individual. To some extent. Based on your answers, I modify my questions. Okay. Sometimes I even tell you before what my first question will be. Okay. Which surprisingly doesn't affect the quality of the answers to that question. So for the registration formalities, you can find a document on the Panda page, and that's it. 2 more things that I want to say. We may move the course from this room to a room on campus, because my group moved from this building to a building on campus. The current number of people we can fit into that room, so we weren't sure yesterday, so that's why we stuck to this room, but we probably can fit it into the other room. Yeah, should work without overcrowding it, so we'll probably move that. Then there are holidays on Thursday too. In this semester next week, I'm not able to give you the exam. That makes 3 Thursdays. We'll find alternative dates for it, so that we'll probably have at least 1 or 2 of these alternative dates that may be a little bit shorter, later in the afternoon or something. If you cannot participate, you will have the videos as well. Okay. Okay, good. Any questions about these formalities? Sounds good. Then one question. So organization, I'll usually take a break after something like 60 or 75 minutes, depending on the material. I want the break not to be right in the middle of a proof. I finish the proof and then I may take a break later or sooner before I do the proof. Then we should be finished by 10:45. Alternatively, we can start a little bit later, 9:30, and finish by 11. I don't care. What's your preference? If you don't have a preference, we start at 8:15. Sounds good? Okay. Good. Then we'll start every week at 8:15. We'll do this break, and then we are finished by 10:45. Okay, the dates and times and rooms for the tutorials you find on Panda as well, and in Paul also. There are 2 tutorials available at this point. Okay, good. If there are no questions, then we'll take a 15-minute break. We reconvene at 9:25, and then I start with the first topic. Okay? Good. I'll see you in 15 minutes. With the course. So the first topic that I will be talking about is perfect secrecy. And let me, one remark before I start. If you studied, if you got your bachelor degree here and studied here and took the course Introduction to Cryptography, some of the topics will seem familiar, like this one, but it's not necessary to have participated in this course, and the way I'll address the topics here will be quite different from Intro to Cryptography. So it's really, the two courses, they don't build upon each other, and this one is a separate course, and it really deals with other techniques to some extent. So it's really not just a repetition. Okay. Perfect secrecy is historically the first concept for security of so-called encryption schemes. It goes back to Claude Shannon, who introduced it already in 1948, 49. It was like, for a long time, it was kind of the standard for security to some extent, but then in the 70s or so, early 80s, things changed quite a bit. But it's still, it's not just historically important, it really gives us a first idea what security is all about, and it also gives us a motivation for what we cover next and why we have to change the security definition. So it's a good starting point for these things, and in some context, perfect secrecy and the concept that I describe here are still used. But first, we have to talk about encryption schemes. So the first part of this course now is about, we want to achieve confidentiality. And to achieve confidentiality in cryptography, we use so-called encryption schemes. And so first, I will give you a definition of an encryption scheme. This will be a preliminary definition. I will modify it later on and make it more precise. But for perfect secrecy, this is the right definition. And as usual, and throughout this course, when I talk about cryptographic primitives, cryptographic constructions, I first give a syntactic definition of these things. What syntax do they have? What are the ingredients? What is the purpose of these different ingredients? I'm not talking at that point about security. That I'll do later on. So encryption schemes, they are syntactically correct. They have to follow the syntax that I said, but they can be good or bad. They can be secure or not secure. I'm not defining an encryption scheme per se as something that's good. Right? Can be good things and bad things. And then I'll define security, what means what is good. But still, I'll have sort of always a correctness requirement in the syntactic definition. So a private key or symmetric encryption scheme pi consists of three algorithms that we call enc, dec, and gen. Encryption, decryption, and generation. And so we write this as a triple here. The key generation algorithm gen outputs a key k according to some distribution on the so-called key space capital K. So there's a key space capital K, which is a finite set. And this key generation algorithm picks an element from this set according to some distribution that is defined also by the scheme, by this algorithm. Typically, in the private key setting, the distribution is a uniform distribution. Everything has the same probability of getting picked, namely 1 over the size of the set K, which makes sense because I always assume that K is finite. Okay? Okay. The encryption algorithm enc on input a key K, little k from capital K, and a message M from the message space P outputs a ciphertext C from the ciphertext space C. And I usually denote this by enc, subscript K, the key is always a subscript, and then M. And the message space is P, the ciphertext space is denoted by T. Okay? These may be finite, they may be infinite. Eventually, we would like P to be infinite, and hence also C to be infinite, namely 0, 1 star. We want to be able to encrypt all possible bit strings of finite length, but it's an infinite space. And the decryption algorithm DEC gets as input a key K and a ciphertext C, and outputs a message M from the plain text or message space. And this is also denoted by M as DEC KC. Okay. And there is a correctness requirement. This is not a security requirement, it's just a correctness requirement. The requirement is that for all keys in the key space and for all messages in the message space, we have that if we first encrypt this message using the key K and then decrypt it using the same key, we get our original message back. So if you first encrypt using a key K and then decrypt using the same key, you get M back. Okay? I'll give you an example in a second. And how do we use that? So you have, say in this context here, let's say you as a user want to store something on a database or share it with somebody else, okay? But nobody else should be able to read this. And you want to transfer that data to here, okay? You don't trust the communication. So what you do is you first, between these two entities, you have to share a key. You have to agree on this common key K. This is done by a secure channel, and I will not talk about this for the time being. There needs to be some way of agreeing on such a key, such that only the two persons know the key. Okay? This is actually a serious problem that we'll address later in the course. Okay? But then once you have this shared private key, if you have here your sensitive data, the plain text or message, I use plain text and message synonymously. It's the same thing, right? Sometimes I say plain text, sometimes I say message. So then you use your the shared private key, you encrypt it. You get a ciphertext. This looks hopefully like something like this, like a random looking collection of symbols. Then you send it over an insecure channel, so anybody can grab this ciphertext. And then on the other side here, you also have the shared private key. You use a decryption algorithm, and you get the original message back. That was a correctness requirement. Yeah? Good. Yeah? So that's how you use these things. So let me give you an example. It's the one-time pad. OTP. And here I assume that I have some natural number n. Say n is some natural number, it's fixed. And then I set key is equal to p is equal to t is 0, 1 to the n. Yeah? Simply the set of all bit strings of length n. This is also often called the one-time pad of length n, because n can choose any n you want. Okay, then the key generation algorithm on input, no, simply not on input. I will do that later in the course on input. Oops. Simply does the following. It picks a key uniformly at random from the set K. And this is the notation I use for that. Okay? Okay, then enc simply, so this is nk of m is simply m XOR k. So the bitwise XOR exclusive OR of the bits in k and m. Okay? I'll give you an example later. And the decryption algorithm on input k, m, oops, is dec of k, c is the same. You simply XOR. So let's give an example. Say we have n is equal to 5, and say m is equal to 1, 0, 1, 1, 1, and k is equal to 0, 0, 1, 1, 0. Then we know that the encryption of m under key k is 1, 0, 1, 1, 1, XOR 0, 0, 1, 1, 0, which is XOR of 1 and 0 is 1. XOR of 0 and 0 is 0. XOR of 1 and 1 is 0. XOR of 1 and 1 is 0. XOR of 1 and 0 is 1. Good. Let me just put here correctness. This follows from the fact that for bit b in 0, 1, b XOR b is equal to 0. And b XOR 0 is b. Hence, if I do this thing here, oops, what I wrote down below there, this here is then, so dec k of enc k of m is, if you look at it, it's m XOR k XOR k, which is m XOR 0 to the n. So if I write something like this, 0 to the n, that means n zeros. Because it's k XOR k, and that is m. And we are done. That's it. Good. If you have any questions, interrupt me. If you think that something I said or wrote down on the board is wrong, let me know. You may very well be right. Okay. Good. So this is the definition, the syntactic definition of an encryption scheme. As I said, this is a preliminary definition. Later on, we will refine that definition. Need more requirements on the algorithms, for the algorithms. Now, to define security, as I said, we'll go to probability theory. Okay? And what we use in the definition of perfect secrecy is, first of all, as I already noted, we have, using the keygen algorithm, we have a probability distribution on the key space. Okay? And I use this notation for this probability distribution, or to denote the probabilities. So the point here, the dot here, will be replaced by a key. And then I say, well, the probability that capital K is, so that I view this here, this k here also as a random variable, as something that picks out something, right? And then that will be a little k then in there. For the definition of perfect secrecy, we also talk about distributions on P, on the message space P. And we denote this by this notation here. So always think of P also being finite. And then there's some probability distribution on the space. But actually, the definition will talk about almost all probability distributions on the space. Okay? So it need not, as I said, for the one-time pad, and in fact, for many symmetric key encryption schemes, this here is a uniform distribution, but here that is flexible. That is, we need to do that. We assume that the two distributions are independent. Okay? Stochastically independent. And that means, I'll write this down, and the reason we can assume that they are independent is because the message space has some distribution. Say you know from the letters in an alphabet, you know that E is somewhat more probable or more likely to occur than an X or Y. Or a T is more likely to occur than a Z. But the keys are chosen independently from that. That's done by the key generation algorithm. It's not done on, you never pick a key depending on what kind of messages you want to encrypt. Never, ever. Okay? So, and the independence then means distributions on PK, independent. That means for all M in P, for all and K in capital K, the probability for picking the message M and picking the key K. Right? So this is the probability of picking, of the distribution picking M, and on the message space picking M, and the probability of the key generation algorithm to pick this little k is the product of the two the probabilities. Okay? That's independence. Conjunction of events is the probability of a conjunction of events is a product of the individual probabilities. Yeah. Okay, let me again give you already an example for this, and then we'll keep going. So that's an example that I will use throughout. Say we have P and T are equal, and they are A, B, and C. And we have a key space which is X, Y, Z. Okay? And now because this is a little toy example, I can define this encryption thing by giving you all possible combinations. And I do that by providing you with a table. Okay? So, and this table looks as follows. So enc K of M. Here we have A, B, and C. Here we have X, Y, and Z. And obviously, what I write down here is the encryption of plain text A under key X, which is B. The encryption of B under key X is C. The encryption of C under X is A. Okay? I'll tell you something, and this is B A and C, and here we have C, A, and B. And I don't give you the decryption, but it's possible because this is correct, because in each row corresponding to a key, we see a permutation of the symbols in P. So if I give you the key X and I give you one of these things, you know exactly what the corresponding message must be, because it's a permutation. If it was not, if you had an A here, and I give you A and X, you don't know whether the plaintext was B or C. And this is true for all rows. It need not be the case for the columns. There is no restriction for the columns, and you see here in this column you have twice B. That doesn't violate our correctness requirement. Yeah? And let me also tell you the probability distributions. And on purpose, I don't use the uniform distribution on K, because then things become too easy. And you won't see a lot, because everything is too easy. So the probability distribution on is the following. The probability of K being the key, that the key generation chooses X is 1/2. And the probability that it chooses Y is the same as the probability that it chooses Z, and that's 1/4. You see the things add up to 1, so it's a legitimate probability distribution. The probability distribution for P, I picked just one. Again, I'll pick here that it's P is 1, A is 1/2, and for the other two things, it's 1/4. It's a quarter. So it's just a toy example. Okay? And then if you want to have like a probability of K, P is, say, B, and K is Z, say, you simply multiply the two probabilities. That's our assumption, or that is our setting. 1/4 times 1/4, which is 1/16. Okay? So that we always do that, and that is by the choice of the key generation algorithm, which is done independently from the messages. Yep. Okay. Once we have that, these two things define a probability distribution on the ciphertext that we see. Okay? What is it? Well, the probability that you see a ciphertext, a certain ciphertext, is a probability of picking a pair of message and key that yields that ciphertext under our encryption rules. Huh? So this is what I said here. The probability, this is induced probability, as I said, on T. So the probability of T being some ciphertext C is the sum over all pairs of messages and keys such that the message under this key encrypts to C. So this is really the probability of seeing that ciphertext under the settings for the probability distributions. And so then we said that this is an end, and by our assumption, we can replace this by this product individually. In each summit, we can replace it by the product. Okay. So let's do our little toy example here. Yeah?
I have a short question about this. So we have two probability spaces. Then
Yes.
we basically construct the product probability
Yes.
space, which gives us independence.
Yeah.
And then the encryption algorithm is basically a random variable which induces the probability distribution of C, right?
Exactly.
Okay.
Yeah. That's exactly what I want. So I said by this assumption, I say the distribution on the product space, on the product of P and K is the product distribution. Independent, by independent, yes. If you are mathematically inclined, yes, that's the way. I don't want to do this all in all mathematical formal beauty. As I said, I assume that you know this stuff, and I will just use it in this way. Okay, let's look here in our example of the probability of the ciphertext being B. Okay? So now we have to look at all combinations that lead to B. And if you look at this table now, so we have to look at this here, and this here. Right? This is where P shows up. So this is the probability of K or P being A and K being X. This here, plus the probability of P being A and the key being Y, plus the probability of the message being C and the key being Z. And now we can use this multiplication rule, right? So probability of P being A is 1/2 times 1/2, right? I use this multiplication rule. Then I have here P being A is 1/2 times 1/4. That's the probability for the key being Y. And here we have 1/4. P being C times K being Z, which is 1/4. And if you add this all up, you get that this is 7/16, right? This is 1/4, 4/16, 1/8, 2/16, 1/16, 7/16. Okay. Okay. Given this, we can look at the following. Once we talk about product distributions or product spaces, right, we can also talk about conditional probabilities. Right? So we can talk about the conditional probability of the message being M conditioned on the ciphertext being C. Okay, so why are we interested in this kind of thing? Before I go into the math, let me explain why we are interested in this kind of thing. We go back to this thing here. So here is a plain text. The adversary can eavesdrop and see the ciphertext. So he knows what the ciphertext is. That's something he can see. And now from the ciphertext, that's a given, that's a condition, that's something he sees. He wants to know what's the message, right? Now he can ask himself, well, if I knew these distributions, if I know the distributions, then I would like to know what's the probability that the message was something given that I see, the ciphertext that I see. Right? And if you didn't have any other information, you would say, well, then my best guess would be the message that has its highest conditional probability given the ciphertext. Right? It would be like his best guess. Right? So that's why we are interested in this conditional probability, because this is the thing that an adversary, an eavesdropping adversary that just listens to what the communication is, sees. Okay? That's his information. And then once it's
But won't they have to know the key distribution for that?
Yes, this is the key distribution is part of the definition. As I said, people always know that the system itself is known, which implies the key generation is known, which implies the distribution is known. And you may also know something, for this kind of security definition, we also know that the plaintext distribution is also known to everybody. Like letters in English. Go to Google and you find the same table all over the place. Right? So this is like common knowledge, and the other thing is really everybody, Kerckhoffs's principle, everybody knows the system except the key. That's the secrets that we have here. okay, including the definition. So that's why we are interested in this definition here. And what is this? Well, we just use the definition of conditional probability. What's the definition of a condition of two events? One event conditional on the other is you look at the conjunction of the two events, the probability of the conjunction of the two events, and divide by the event on which you condition. That's the definition of conditional probability. And then I can look at the following thing here. What is this definition here? What is this expression here? Right? It's the probability over all pairs m, k, such that the message is m and the ciphertext is is c. Right? But that is the sum over all, because the message now is fixed. Here, I want it to be m. Then this here, t is equal to c, is only now the sum over all keys, namely those keys that encrypt m to c. Because I have a conjunction here. It must be m. So this here is fixed now, it's m. And then only this over the sum over k stays. Okay, so I can reformulate it in this form. And then again, I use the independence of the distributions to make that into the product. Okay, so let's do this here for a little example. Again, by the way, here I obviously need to assume that the probability of the ciphertext being C is non-zero. Yeah? Better not divide by 0. Okay, so let's look at an example here, which is, I use the example from the other board. So I want to look at the probability that P is A conditioned on T being B, okay? Which is the probability of P being A and T being B divided by the probability of T being B. Luckily, we already computed this numerator, right? Denominator, sorry. Okay, so now we need to compute this thing here. So this is the sum over all k such that the encryption of A under k leads to B. And then I need the probability of P being A times the probability of K being K. Just using my little observation over there. Yeah. So now we just look at this thing. So the probability of P being A, that's something that we can pull out, right? This is the same as the probability P being A, because this is independent of the summation. It's only over K. And then we just sum up over all K's such that the encryption of A under key K leads to B. The probability of K being key being K. So which keys encrypt A to B? Which keys encrypt A to B? And you see there are two. right? Here, and this here, right? These are the two keys that encrypt A to B. So this is then the probability. Here, probability of P being A is 1/2 times the probability of K being X plus the probability of K being Y. Right? Y, and this is 1/2 times 1/2 plus 1/4. Okay, and if I didn't make a mistake, this I always forgot in all of my lines here. So we can keep it here. Probability T is B, which is now 1/2 times 1/2 plus 1/4 divided by 7/16. Okay? Which is, if I did that correctly, this is 3/8 divided by 7/16, because this is 3/8. And now we get that this is 6/7. 6 because the 7 here, the 16 becomes here 2, so it's 6/7. Okay, good. So this is how we calculate all these things. Now, what would be like the best thing that you can imagine about security? And go back to this picture and go back to your question. The adversary knows the distribution on the keys. He knows the distribution on the plaintext. All right? So the best thing is that we could hope for is that observing the ciphertext doesn't give him any additional information. And what does that mean? Any additional information. So my favorite example is, when did you not get any information from this course? Then the probability of answering questions correctly before and after the course is the same. Right? Because then the course didn't make any difference to you, right? Okay? So and that is often what we call the a priori distribution on your answers. The thing before you listen to the course is something that we knew before. It's the same as the a posteriori probability, namely the probability after the fact, after the course. Right? So that means, and in this case here, it means that the probability of M conditioned on the ciphertext is the same as the probability of M without conditioning on the ciphertext. The two probabilities are the same. The probability of you answering correctly before and after a priori, a posteriori are the same. That is perfect secrecy. So here we go. And we say that, and there's one more thing, we don't want to talk about the distribution on the plaintext being something specific. We want that to be true for all distributions, no matter what kind of a priori information you may have or not have. Okay? And that leads to the definition, going back to Claude Shannon, as I said, of perfect secrecy. So a private key encryption scheme pi, consisting of our three algorithms with key space K, message space P, ciphertext space P. T is perfectly secret if for every distribution on P, every M in P and every C with, and here I included this condition that the probability better not be zero. Probabilities are positive, non-negative, so now we want to be positive. We have that the probability of P being M after seeing the ciphertext is the same as the probability of seeing M without knowing what the ciphertext is going to be. And we want that to be true for every probability distribution. We don't want to make that, well, it's true for some and not for others. That would be too application dependent, because the applications usually depend what kind of distributions you have on the messages, right? If the distribution on digit sequences, if you use a credit card number, is different from if you just pick them randomly, because credit card numbers are not random, uniformly at random. So that the distribution on the plaintext is usually application dependent. And we want that to be true for no matter in which application you apply a perfectly secret encryption scheme. That's one of the common trends that I will also insist on. Encryption schemes or cryptographic techniques should be secure no matter what the application is. You don't want to do them application specific, at least not in the very beginning. Okay, so this is perfect secrecy. Question, is my toy example perfectly secret? Why not?
Because the probability of P equals A is 1/2, and we just calculated it.
Yep.
That's 6/7.
Yeah. So probability of P being A conditioned on this ciphertext is 6/7, whereas the probability of A unconditioned is 1/2. And 1/2 is not equal to 6/7. So, which has a very clear interpretation. If you see the ciphertext B, then it's more likely that the plaintext was A than it was before you saw the ciphertext. So it increased the probability, which means the ciphertext contains information about the plaintext. If your probabilities of giving correct answers increases after the lecture gave you some information, okay? Which I still hope is true, but anyway. Okay. So underlying this, but I don't want to go into the details, is really a theory of information theory, which goes back to Claude Shannon. So, and you could formulate this or one way to rephrase this is ciphertexts do not contain any information about the message. And then it's perfectly secret. Okay, good. Yeah?
What is the significance of like this being 6/7 over it being something like 1/7? Like if the probability falls,
Yeah.
does that mean that this is not this ciphertext does not belong, correspond to this message?
If this was below 1/2, this means, again, the ciphertext tells you something about the plaintext. Yeah. Namely, it's less likely that it was A before, because probabilities add up to 1, some other plaintext must have a higher probability than it had previously, before seeing the ciphertext. Yeah. Because the conditional probabilities, if you condition on this fixed ciphertext, the conditional probability over all plain text must be 1. So if one gets smaller probability, another must get a larger probability. But even if you, if you would give had a smaller probability of giving correct answers, and assume that the answers are just 0, 1, yes, no, flip the answers. Yeah? Being always wrong is as good as being always right. Just flip it. Yeah? don't take that too serious, right? But I mean, in the sense of just flipping things, and this is something that we sometimes do. We may, without loss of generality, assume that things are larger than 1/2. Because if they're smaller than 1/2 and we just output bits, just flip it, and you get one larger than 1/2. Okay. Okay. Good. Let's, we want, so the disadvantage of this definition is that it has this quantifier over all probability distributions. So it's hard to check. Going over all probability distributions on a space that has, even if it has finitely many elements, the number of probability distributions is infinite. It's even uncountable. It's a mess. It's hard. You cannot check it so easily. So we would like to have a characterization of perfect secrecy that avoids talking about all probability distributions. Something that we look at it, do a few calculations, bingo. We know the answer. It's either perfectly secret or not. Okay, so we want to get rid of this conditioning or quantifying over all probability distributions. And we'll actually achieve that. And to do that, we need one fundamental lemma and a little notation. And then we can go on. So for every message and every ciphertext, I denote by the probability of M being encrypted to C. And that's why I have here this K. Okay, being encrypted at all over the choice of the keys. So this is not a little k, it's really the calligraphic k for the ciphertext. This is simply the probability or the sum over the probabilities for all keys k that encrypt M to C, and I sum them up. Okay? So it's really like, if you give me M, what's the probability of getting the ciphertext C? It's this sum over there, the sum over all keys that encrypt M, the sum over the probabilities of all keys that encrypt A to C, M to C, sorry. Yeah? So that's why I have here this K, script K for the space, and here I have it for a specific key. So this is basically what we did here, right? This part here, in here. This is exactly what I did. But because here I also had this P is equal to A, I had this product, this factor in front, which I usually forget if I do this example, but this time I well managed. Okay? Good. So, and using that notation, we have the following lemma, a fundamental lemma. We use our private key encryption scheme with the usual sets. We let P, this thing here, be a distribution on P, some distribution. And for every C in T and every M with the probability that M appears really. So if you have a probability distribution where M, the probability of M is 0, it simply never shows up, right? Because we are talking about discrete probabilities. Then we say that this probability here that I defined here is, in fact, the probability of having the ciphertext C condition on the message being M. It's quite, if you know a little bit about probability, well, this is actually by definition. This is it. Right? But just let me just do the calculations so that you see, get a little bit used to this formalism. So here we go. Proof. Lemma 1.3. We just calculate these things. So the probability T being C conditioned on P being M is the probability of T being C and P being M divided by the probability of P being M. I'm allowed to do that because this is non-zero. Okay? So this is, what is this here? This is the sum over all keys such that the encryption under key M is C. And this is now the probability of P being M and key being K. Right? It's the same thing. Right? And this here, because we can use our, this here is the same. We multiply the probability of P being M times the probability of K being K. Oops, I forgot. I just was wondering why this was true. Thank you for your hint, because this helps me quite a bit. Because now what we have is this probability shows up in every summand, so we just cancel it. And this is exactly our probability of the encryption being C. Right? So this is simply. And that's it. Okay. Yeah. Okay. And given that, we have the following equivalent characterization of perfect secrecy, namely a key encryption scheme pi is perfectly secret if and only if. So it's equivalent. For every two M messages, M0, M1 in the message space, and every ciphertext, the probability that M0 encrypts to C is the same as the probability that M1 encrypts to C. Right? Which also tells you, like, C doesn't tell you anything about the messages, because for all messages, the probability of getting that encryption, if that was a message, is the same. And the big advantage of this, obviously, being I no longer talk about distributions on the message space. Because this here is just something about the distribution that's on the keys. Right? My definition here, if I go back, this here is only using the distribution on the keys, no distribution on the messages. Okay? And that translates immediately to this equivalent characterization. Okay, let's prove this lemma. Good. So, can I erase this? If you do not So this is the proof of, yep. So proof. So we have to prove two directions. The first direction is, which one do I prove first? I don't mind. So I go this direction. What does it mean? If I have this condition, then the scheme is perfectly secret. Yeah? Okay. And I distinguish two cases. Case A is, okay, so we look at the probability of P being M conditioned on T being C, where P is some arbitrary distribution on P. Okay? And then we look at this thing here, and we would like to prove that this is the probability that of P being M. So we look at two cases, namely the probability of P, the M in P is 0. I don't want to say too much about this. This is easy. Check yourself that this is true. Everything's 0 in that case anyway. Okay. And then we have the case where this is non-zero. Yeah? So let's do the case B. The probability for P is M is larger than 0. Okay? Strictly positive. So now let's look at need to show the probability of P is M conditioned on T being C is equal to the probability of P being M, because that's our defining property for perfect secrecy here, right? For every M and C, and I condition on and but we need that the probability of T being C is larger than 0. Okay, so let's look at this term here. Probability P is equal to M condition T is equal to C, which is, what is this? So I'll just write this down as usual. Probability of P being M and T being C divided by probability T being C. Okay, I can do that because I know that this thing is positive. Okay, then what can I do? Then by lemma 1.3, we know that this here, if you go back to lemma 1.3, this here is really 1.3 is really, let me just do that. This is the probability of M encrypting to C is equal to C times the probability of P being C divided by the probability T being C. Right? Because by conditional probability, if I multiply this by the probability of M, I get the probability of T being C and P being M. Okay? That's just by conditional probability and using this lemma here. Okay. And this again is this here. Okay. Good. Now let's look at this numerator here. So what is this probability of t being c? So this is the sum, and here I now use the total probabilities. What's the sum of getting c? Or what's the probability of getting c? It's the sum over all messages that encrypt to c. So this here really is the probability of t being c and p being m prime, and I use the summation over all m prime in p, actually. Okay? So what I do here is I partition the event of getting ciphertext C. I partition it into disjoint sub-events. Namely, the sub-event, the ciphertext is C, and the message was this. Ciphertext is C, and the message was that. Ciphertext is this, C, and message was that. And these are disjoint sub-events. Right? So for different M prime and M double prime, these events are disjoint. And hence, the probability of the union of disjoint events is the sum of the probabilities. And that's what I use here. It's a trick that I use all over the place in this course. I have an event whose probability I need to analyze, and I partition that into a set of disjoint sub-events that I analyze individually, or that I can easily analyze. Okay. So, and how do we continue here? Well, I use again conditional probabilities. So this is, let me just write m prime here. Now probability of, and now I use t being c conditioned on p being m prime times the probability of p being m prime. Okay. This here is by my little lemma here, is the sum over all m prime, the probability of getting encryption t, of m prime encrypting to c times the probability of p being m prime. This term here is this here. Now, but here now I use my okay. Yeah. Now I use my condition, which I haven't used so far. For any two things, these two probabilities are the same. Right? If it's true for pairwise, then it's true for all of them. So all these things here I can replace by the probability that M encrypts to C. Okay. If it's true for any two are the same, then they all are the same. Okay, so then I can rewrite this as the probability of encrypting M to C times the sum the sum overall m prime, the probability of P being m prime. But this year, the probability over all messages must be 1. Right? If I add the probabilities over the whole probability space, I get a 1. That's probability. So this here is 1. So this here really is the encryption, the probability that I encrypt M to C. Okay? Good. So now we are done with this part. Because this here is this year. Okay? But here, so now I can replace this here by the probability of T being C. Right? And then I can, this and this cancels, and I have this and this is the same. And I'm done. Okay. I won't prove the other direction because it's easier even than that. You just plug in the things that the equalities, and then you're done. Okay. Again, using the trick that you can here the other direction you have to start out with the perfect secrecy, and then we can get this. Okay, and okay, good. Yeah. So we have this important property that the encryption, if we have perfect secrecy, the probability that a message encrypts to a certain ciphertext over the choice of the keys is for all messages the same. No matter whether you have this message or this message over the choice of the key, the distribution on the resulting ciphertext is always the same. And hence the ciphertext doesn't tell you anything about the message. Okay. And if you go back to the one-time pad, the one that I had in the very beginning, here I have the length with L, all these things, you can easily check that it's perfectly secure. Or it's perfectly secret. The reason is that this probability of a key, that a message is encrypted to some ciphertext, let's go back to it. See that briefly. So in the one-time pad, we now use this characterization, right, that we have here. So fix M, C in 0, 1 to the L. And we need to look at what's the probability that we encrypt M to C. And this is the probability that over the choice of the key, that M XOR K is C. But that is the same as the probability over the choice of the key that X or M on both sides. That K is equal to M, X, or C. X or K on both sides. But this year, in the one-time pad, we pick keys uniformly at random. This is a given M and C, this is a fixed value. This is a fixed bit string. So the probability that K under the uniform distribution is this particular bit string is 1 over 2 to the L. Because that's the size of the key space. And that's independent of M. So for all M, it's the same. And that, by our previous lemma, says that it's perfectly secret. Yep. Now comes the bad news. This goes back to Shannon. It says that if we have a private key encryption scheme such that all the key space, the message space, and the ciphertext space, then pi is perfectly secret if and only if key then chooses every key with probability 1 over k, and for every M and C, there's a unique key such that M is C. Unfortunately, that implies that if we want to achieve, it also said that if this here is too small, smaller than the message space, you won't get perfect secrecy. It's impossible. Right? You must have that, then it says it must, and this keys to encrypt a message must be as long as the message, unfortunately. You can use keys, and that also means you can only use a key once. If you use it, because otherwise if you use it twice, then the key is no longer as long as the message, right? So if you want to encrypt a message of 1 gigabyte, you need a key of 1 gigabyte that you sort of have to share before you can use it. Impractical, forget it. Well, limited practicality. The one-time pad was used for the so-called red phone between Washington and Moscow during the Cold War. They used the one-time pad for the communication between these two things. The red phone was meant to prevent an atomic war, so that they could just call each other and say, okay, unfortunately, we just fired an atomic bomb. It wasn't meant to be. But also, they used it for that. It was just highly secure. But so it has applications, but in like e-commerce, e-banking, you cannot use it. Okay. So we need to do something else. Right? So it's nice, but it's not, it's impractical. And sometimes it's also not good enough. So it's expensive, but sometimes it's also not good enough. Because what it talks about is attackers that just eavesdrop. That just, they look at the ciphertext and try, given the ciphertext, they try to recover the message. But attackers may be much more clever. They may actually force or entice you to send certain messages and encrypt them, and they are not interested in that message, but they are interested in other messages that you use, for which you use the same key. And I will tell you a little bit about practicality of such things in the next lecture. But it's it's expensive, and sometimes it's not good enough. But it also talks about all attackers. And usually, I mean, attackers can be very powerful, but they still have limited resources, right? Time is limited. Eventually, the sun will stop shining, and then, you know, in any case, I mean, if my credit card number, if you get hold of my credit card number in 50 years, I probably don't care. I personally don't care, right? And my credit card number is no longer valid anyway. So we talk about limited lifetime also of applications and information. Okay. So maybe, and the last thing I want to briefly mention today, and I will pick it up again when we meet again in 2 weeks, is we can have yet another formulation of perfect secrecy, an equivalent one, and that characterization of perfect secrecy really leads to the modern definitions of security for encryption schemes. And I just want to briefly talk about this a little bit. Probably also need it for the tutorials, not a little bit. And so we, cryptographers tend to have two characteristics. The first one is they are paranoid. They always think about people who want to attack something. And they are like little children. They like to play. And hence, the way they define security is by playing games. Okay? And then looking at how can you win this game, or how can somebody win this game. Okay? And this is a way, a game to define perfect secrecy. And it turns out that this game, appropriately modified, gives us the modern definitions of security. Okay? And so we always have, in such games, for encryption schemes, we fix an encryption scheme for which we want to define, say, in this case, perfect secrecy. And then we have two players, a challenger and an adversary. Okay? And here's the game. It's called the eavesdropping indistinguishability game. And it has here this funny acronym, but it's the A is the adversary, pi is the scheme, E is for eavesdropping, and is for private, and K is for key. Okay, so, and so the challenger does the following. It chooses a key K with the key generation algorithm. And then the challenger challenges the adversary. They said, look, if you are so clever, as you claim to be, you should be able to do the following. You give me two messages, M0 and M1. And if I encrypt one of them, if you're really clever, you should be able to tell me which one I encrypted, if I just give you the C, but not the key that I used. Right? And this is actually what we do. So C, the challenger chooses a key K. A outputs two messages. C now picks one of the two messages uniformly at random, both with each one with probability 1/2. And it encrypts the chosen message, which is characterized by this B, encrypts this, and sends this C to A. And now A's challenge is to guess or compute which of the two messages that he picked beforehand, so he knows which ones they are, C encrypted. So he outputs a bit B prime, and we say that the result of the game is 1, or the adversary wins, if B prime is equal to B. So if A correctly predicts or guesses which of the two messages C encrypted. Yeah? Otherwise, the result is 0. Okay, so this is a game. The challenger challenged this adversary. Give me 2 messages, I encrypt one of you, and so you will not be able to tell me which one I encrypted, if it's a good pi. Okay? And this is what we, so this is the schematic view. So first we choose the key, then we pick the messages on A side, then we pick the B on C side, we encrypt and send C over, and then we get B prime back. I fill this out later on with kinds of all things when I talk about reductions, and this picture will get more crowded. Okay? And what we can say is, and prove, is that a private key encryption scheme is perfectly secret if and only if for every adversary, the probability of winning the game, of the output being 1, is exactly 1/2. Which means the C doesn't even help him, because that he could have achieved without seeing the C. Just pick a bit uniformly at random. Right? Okay, so this is why this is kind of quite intuitive that this is at least implied by perfect secrecy. And why is it so that this is equivalent to perfect secrecy? Well, the C shouldn't give you any information about the messages. Why is it implied by perfect secrecy? Because of this characterization here. What I give to you in the game as a challenger is stochastically independent of M, 0, M1, of the bit I picked. Because the C's that I sent you have the same probability distribution, whether I pick M0 and encrypt it or M1. Doesn't matter. And since that is true for all pairs, you can even choose the pair. I don't care. Right? So that's why these things are equivalent. Okay? And this will be our, this game, the experiment, that will be our starting point to do better definitions of security that lead to practical schemes and look also at more powerful and more advanced adversaries. In some sense also restricted adversaries, but justified limited adversaries. Okay, good. That's it for today. We meet again in 2 weeks, and it's probably being in the O4 floor on campus, in the O building. Okay, thank you, and see you again in 2 weeks.